So in this lecture, we will discuss some basic numerical problem which are related to some basic circuit analysis, right? So this lecture will discuss some numericals which are based on source transformation, current division and voltage division rules, and then resistances in series and parallel. So let us start with some numerical example related to source transformation. As we know that a voltage source, you can convert or transform, uh, can be transformed into a current source. Similarly, a current source can be transformed into a voltage source. Okay, so these two can be transformed into one another. We can have an equivalent of a voltage source which is current source. We can have an equivalent of current source which is the voltage source. Now to transform the two types of sources into one another, for example, if you want to transform a voltage source into a current source, so the basic condition that is required is that the voltage source must have a resistance in series connected to it apart from the load terminals. So the this you can say are these are the load terminals. So apart from these, this particular circuit diagram can be transformed. So this can be transformed into a current source with a resistance in parallel to it. So this resistance is the same resistance as uh, connected to a voltage source, means R. This R will come as it is here, and then you have the load terminals, right? So these are the load terminals, and this part is the transformed part of the voltage source, and the value of I current is equal to V by R. So this V is the same, this one, and this R is the resistance, this one. Okay, so vice versa is also true. For example, if you have a current source and a resistance in parallel to that current source, that can be transformed into a voltage source with a voltage which is equal to IR, and the parallel resistance will be connected in series with the voltage source, right? But please do not change the load terminals. They will remain unaffected, unchanged. Means whatever transformation we are doing, we will do across the load terminals. We will not change the load terminals, right? So in this question, we have a voltage source of 72 volt, and then a resistance of 4 ohm connected in series with that voltage source, and then we have a load resistance which is of 6 ohm. So that means these two terminals are supposed to be load terminals, right? These two terminals are load terminals. So This is load. So now the first thing that we should see when we transform a voltage source into current source, and that is we must check whether there is any series resistance in falling with the voltage source or not. Okay, only then we can transform the voltage source into current source, right? So this part, so this part of the network is to be transformed. So this is what we will transform. Okay, so we will have an equivalent current source here. Okay, and the direction would be upward. Okay, the direction depends upon the direction or the polarity of the voltage basically. If this is how the voltage is connected, so the current source will be shown like this. And similarly, if the voltages are shown opposite, means minus plus, then the arrow would go downward. In case of current, this is current source, this is voltage source, right? And similarly, this is current source and this is voltage source, right? So you can have the equivalent current source with a value I is equal to 72 by 4, in this case ampere, and then resistance of 4 ohm will be now connected in parallel to the current source, which was earlier in series with the voltage source. And then you have a 6 ohm resistance, which is the load resistance. So you can see I have not changed the load resistance. Whatever changes we have been made across the load resistance, right? So this part is the transformed part, right? So here this is 18 ampere I. So you can redraw this one properly. So you have 18 ampere current source, and then you have a 4 ohm resistance, and then you have a 6 ohm resistance, right? And then this is load branch. Okay, so this is the uh, equivalent of the given voltage source, right? So this is the equivalent voltage source. Now let us consider one special case here. We can have a network with a battery wherein we do not have a series resistance. Okay, we do not have a series resistance. We can have a network like this. So this is, let us say, what you call as the load terminals, and this is a load resistance. This is a load resistance 6 ohm, and this is, let us say, 4 ohm, and this is 72 volt. So now can we transform, so my question is, can we transform this voltage source into an equivalent current source? So let us check this. The first thing is that we do not have a series resistance here in this case. There is no series resistance with voltage source, that is R is equal to 0. Now the equivalent current source is I is equal to V by R, or 72 by 0, that is infinity. So I is equal to infinity is something not real. This is not real. So that means we cannot transform such voltage source into equivalent current source. So this is one special case here, right? So we can also have a network. In the same case, if we consider, like, for example, if you have a voltage source and a load resistance. So okay, so we'll consider one more special case, like we have a voltage source VDC, and then we have the load resistance. So this is load. Now, can we transform? Can we transform this part? Can this be transformed? The answer is no. The reason is same. Okay, the reason is same. So these two are same cases. So it cannot be transformed, right? Now let us come to the another example wherein we have to transform a current source. So transform the given current source into an equivalent voltage source. Now what we have to take care of while converting a current source into voltage source, we must check whether there is a resistance which is falling in direct parallel to the current source, as it is in this particular case. Now these two elements are in pure parallel. How? Because these two elements are sharing the same junctions. You can also draw it like this. So these two nodes are same nodes, right? So this can be transformed. This current source can be transformed into an equivalent voltage source, right? So this is 6 ampere, this is 2 ohm, and then you have load terminals. Now we have to transform this part of the network only. We will not you know touch the load terminals. Okay, we will only transform this part is to be transformed. Now the transformed circuit is, you have a voltage source which is equal to V is equal to I into R, and that R is here, and then you have the load terminals AB, right? So in this case, I is equal to 6 ampere, R is equal to 2 ohm, so V is equal to 12 volt. So this is 12 volt and this is 2 ohm. So this part is the transformed equivalent of the given current source. So this is how you can transform. Remember one thing, that to transform a current source into a voltage source, it must have a resistance other than the load resistance connected in parallel to it, that is current source. Okay, for example, there is a current source and a series resistance of some value, let us say Rs, and this is I, and then you have that 2 ohm resistance connected here, and then you have the load terminals. Okay, now my question is that can we transform this part? Can this part be transformed? The answer is no. Why? The reason being that you have a resistance which is in series with the current source. Okay, so this cannot be transformed, because in this case these two junctions are at different, these nodes are at different potential. So hence 2 ohm and I are not in parallel, and that is why we cannot transform the current source in such case. Now let us come to one numerical which is related with the series combination of the resistances. So when some resistances are connected in series, the equivalent resistance is basically the sum of all the resistances, right? So equivalent resistance, what is equivalent resistance? For example, you have a network like this, Let us draw a complex network like this. This is a complex network. There is only one source, voltage source, and all other are passive network, passive elements, sorry. So this will distribute some current, deliver some current to the given network. This whole network, from this whole resistive network, can be replaced by a, this can be replaced by a single resistance known as equivalent resistance. Now when your elements are connected in series, so the equivalent resistance here is sum of these three resistances. Sum of these three resistances, right? So the first part is asking about the equivalent resistance of the network. So in this case, the equivalent resistance is sum of all the resistances which are connected in series in this particular circuit across the input terminals. Now, which two terminals are the input terminals? These two terminals are the input terminals where your battery is connected. So that means you will measure, you will replace all these five resistances with a single resistance which is called as equivalent resistance, and in this case the sum of all these resistances is equal to 90 ohms. So R equivalent is 90 ohm, right? The second question, second part is basically the current through each resistance. Now in this case, all the elements are connected in series and they will have the same current, right? So the answer to this second part is all resistors will share same current. And what is that current? It is that I. So I is being delivered by this battery. It will go to this branch here and it will be same in all the resistances. So I is equal to V by R equivalent. So it is 9 by 90, 9 volt by 90 ohm. So I is equal to 0.1 ampere. So the answer to this is 0.1 ampere, and answer to the first part is 90 ohm. Now what is the potential drop across each resistance? And this is also again very easy. Now how do we calculate the voltage drop across each resistance? So now this resistance, this current will go and flow in this branch and it will go to this particular resistance. This resistance has certain value. The by sign convention you have the polarity across this resistance like this, that the same current will reach to R2 and will have a potential like this. Then same current will reach to R3 and it will create a voltage drop across R3, and the potentials can be shown like this, polarities can be shown like this. Then the same current is going to R4 and you have voltage across R4. Then the same current is going to R5 and you have the voltage drop like this, and then same current will go to the negative terminal of the battery. This is I. So that means the voltage across any resistance is the product of that resistance and the current through it, right? So let us see. Hence you can say that the voltage across R1 is, so the voltage across R1 is equal to V1 is equal to IR1. So V1 is equal to 0.1 into R1 is 20 ohm. So it is 2 volt. Similarly, V2 is equal to IR2, which is 0.1 into 20 is equal to 2 volt. Then V3 is equal to IR3, which is 0.1 into 20 is equal to 2 volt. V4 is equal to IR4, 0.1 into 20 is equal to 2 volt, and V5 is equal to IR5, which is equal to 0.1 into 10 volt, because R5 is 10 ohm, sorry, 0.1 into 10 ohm, R5 is 10 ohm, so it is equal to 1 volt. So you can see the sum of all these is 2 plus 2 plus 2 plus 2 plus 1 is equal to 9 volt. Okay, and the input voltage is also equal to 9 volt. Hence it is also proved here that the applied voltage will be divided across each series element according to its resistance. Whatever is the resistance of the series element, according to that resistance and the current through that resistance, we will have a certain voltage drop across that particular element. Now we can also calculate the voltage across any series element, can also be calculated using the voltage division rule. And what it says, for example, if you have to find out, if you have to calculate the voltage across the resistance R1, if you have to calculate the voltage across resistance R1, what you will do? You will apply voltage division rule here. And what does a voltage division rule state? It says that if you have to find out the voltage across this particular resistance, which is, let us say, V1, okay, so this voltage will be equal to the applied voltage into this particular resistance and sum of all, divided by sum of all the resistances which are connected in series. That means V1, sorry, and that means V1 is equal to the input voltage into the respective resistance R1 and divided by sum of all the series resistances. So it is equal to 9 into 20 divided by, what is the sum of all the series resistances? It is 90 ohm. 20, 20, 20, 20, 10, 90 ohm. Right? So it is 90 ohm. So this is 10, 2. So V1 is equal to 2 volt. Okay, in this way we can calculate the voltage across any series element using voltage division rule also, right? Now let us come to the parallel combination of the resistances. Now, when do we say that the circuit or the elements are connected in parallel? When all the elements which are connected in electrical network share the same node. So you can see all these nodes are at same potential, right? Because they do not have any voltage drop in between. What does it mean? It means that, for example, if you have, let us say you have a resistance connected here of some value, let us say 1 ohm, for example 1 ohm. In that case, this is, let us say, node A, this is node B, and this is node C, then this is node D. So in this case, these two nodes B and C, these nodes are at different potentials or potentials, right? How? Because whatever voltage you have here, let us say you have a voltage VB here and you have a voltage VC here. So so this VC is equal to VB minus the voltage drop I into 1, because 1 ohm is this resistance, and let us say I is some current flowing through this particular branch. For example, I is the current flowing through this branch. So that means these two voltages are different now, and when these two voltages are different, we will say that these two nodes are at different potentials, and these two nodes are not same nodes, right? So in that case, this is not a pure parallel circuit. In that case, it is not a pure parallel circuit. Now, let us see this. Now, if we have to find out the equivalent resistance, because all the resistances are connected in parallel to one another, so 1 upon R equivalent is equal to 1 upon 20 plus 1 upon 100 plus 1 upon 50, and this is equal to 12.5 ohm, right? So it is 12.5 ohm. Now the current through each resistor. How will you find out the current through each resistor? How do we find out the current through each resistor? Simple. Either we can use volt current division rule, or we can use a simple fundamental. Like, for example, if I is the current here, and this current will be divided into all these three branches depending upon the resistance. Let us say this is I1, this is I2, and this is, let us say, I3. So now, because these resistances are in parallel, hence they all will have same voltage applied to each resistor. That means I1 is equal to V upon R1, I2 is equal to V upon R2, and I3 is equal to V upon R3. So it is equal to 125 divided by 20, 125 divided by 100, 125 divided by 50. And this will be your 6.25, and this is your 1.25, and this is your 2.5. Ampere, ampere, and ampere. So you can see that the voltage is same. This is the concept of parallel circuits, right? Now the third part in this is, it is asking about the potential drop across each resistance. So potential drop, as we have already mentioned and said, that because all these are in parallel to one another, so the voltage will be same, 125 volt. Here I1 is 6.25 ampere, I2 is 1.25 ampere, I3 is 2.5 ampere, and The equivalent resistance is 12.5 ohm. So these are the answers. Now, let us see this particular circuit. In this circuit, we have a complex combination of all the resistances. They are neither in series or parallel. Means there is a combination of series and parallel. All right. So how to solve such network? So in such network, you can find out the series resistances first of all, like it is solved here. So this is R3 resistance, this is R4. So the combination of these two resistances, because these two are in series, so the combination is 6 plus 4, which is equal to 10 ohm. And let us say we have given a new name to this resistance, which is R34. It is a notation given, right? Notation. So let us redraw this circuitry. So by redrawing this circuitry, you have this one now. R2 is as it is, and these two resistances have been replaced by a single resistance, which is 10 ohm. So now you have 10 ohm and 10 ohm in parallel to one another. So 10 ohm and 10 ohm, what is the, let us say it is 1 upon R dash, 1 by 10 plus 1 by 10. So it is R dash is equal to 100 divided by 20. So it is 5 ohm, right? So R234, because this is R2, this is R34. So the new notation given here is R234, which is equal to 5 ohm. Now from here, see what we are doing, if you have noticed, we are simplifying this network from end to beginning. So this is the beginning of the network where your voltage source is connected. It is taken as the beginning, input of the network, right? So we are moving from last resistance to the first resistance, and this is how we are simplifying it. We should not go from first to last. We should not go like this. No. Okay, we have to simplify it from last to front first. Okay. So now these two were in series. The combination of this is was in parallel to this one, and then you have this resultant network here, right? So here you have these two resistances in series with one another. So the equivalent resistance you can see. So we have not changed this 24-volt source. We have moved from last resistance to the first resistance, and we have simplified the given network. So the equivalent resistance is 12 ohm, right? Now we can use the voltage division rule also, okay, because these methods are used for simplifying the electrical networks, right? So let us draw the circuit as per the statement given here. You have two resistances which are connected in series with one another across an 100 volt sorry source. So this is R1, which is 25 ohm. This is R2, which is 50 ohm given, and this is VDC, which is 100 volt, right? So let us say some current I will flow here. This current will go to this resistance, and as per sign convention, you have the polarities like this here. And let us say V1 is the voltage here. The same current will flow into the resistance R2, and the as per sign convention, you have plus and minus, and V2 is the voltage drop here. So as per the voltage division rule, voltage drop across R1 is V1 is equal to the input voltage V into that very resistance R1 where you are calculating the voltage drop, and divided by sum of all the series resistances. So how many series resistances are there? R1 and R2. So R1 plus R2. So this will give me, so let us solve it. 100 is the applied voltage into R1 is 25 ohm, and then R1 plus R2 is 25 plus 50. So V1 is equal to 100 into 25 divided by 75. So 25 3 is 75. So 100 by 3 volt. Similarly, you can find out the voltage V2 across. So V2 is equal to the input voltage into the resistance where you are finding the voltage, that resistance in this case is R2, and divided by sum of all the series resistances, that is R1 plus R2. So it is 100 into 50 divided by 25 plus 50. So V2 is equal to 100 into 50 divided by 75. So it is 200 by 3 volt. So this is how you can find out the voltage across each series element using voltage division rule. Now let us come to the next part, which is current division rule, and let us draw the circuit according to the statement. There is a current source which is of 3 ampere. There is one voltage source which is of R1 is equal to 10 ohm, and then you have one more resistance. There is a current source 3 ampere, one resistance R1 10 ohm, another resistance R2 which is 20 ohm. Now you have to find out the current through each branch. So let us assume that I1 is the current in this one and I2 is the current in this particular, and the total current is I flowing here, right? Now, as per the current division rule, if you have to find out I1, now see, if you have to find out I1 can be calculated, as we have already discussed this in theory class. I1 can be calculated by multiplying the resistance of the opposite branch, this one, with the main current. Like I1 is equal to main current 3 ampere into resistance of the opposite branch is, it is 20 ohm. So it is 20 ohm, and divided by sum of all the parallel resistances, right? So how many parallel resistances are there? 10 plus 20. So this is ohm and this is also in ohms, right? So you have 3 into 20 divided by 30. So it is cancelled out here. So 2 ampere is the current, right? This is the current in I1. So out of 3 ampere, 2 ampere current will flow to this particular 10 ohm resistance, right? Now how will you find out I2? I2 is equal to the main current. So let us find out I2. So similarly, I2 can be calculated using CDR. Now what is I2? I2 is the main current, that is 3 ampere, into resistance of the branch which is opposite to that of I2, and that branch here is 10 ohm, divided by sum of all the parallel resistance, 10 plus 20. So it is 3 into 10 divided by 30. So it is 1 ampere. So I1 is equal to 2 ampere and I2 is equal to 1 ampere. So let us go back to the circuit diagram, and we can see that because R1 is less than R2, hence I1 is greater than I2. So this is how we find out the current using current division rule in parallel circuitries, right? So in this particular lecture, we have discussed about the source transformation. We have discussed about the series resistances and parallel resistances, equivalent resistance, current division rule, and voltage division rule. Okay, these analyses, they are very basic analysis. Basically, they are very basic analysis, and all these methods are used to simplify the complex networks. You will require the knowledge, the basic knowledge of these small little techniques to simplify the complex electrical networks. Okay, so practice more numerical problem on these topics. And thank you so much.